All right, our second speaker for today is Ivano Basile from the University of Mons, and he will talk about emergent strings with broken supersymmetry. Please go ahead, Ivano.
All right, thank you very much. And also thanks a lot for the kind invitation. So I'm going to talk about this paper. The archive number is written here. And in order to try to be as brief as possible, I'm going to focus on a very specific point. So I'm going to describe infinite distance limits in string models where supersymmetry is broken at the string scale in particular. So I'm going to describe some constructions in some specific models that involve branes. And the punchline is that within these constructions, we find two possible infinite distance limits. And it turns out that one of these limits is always at the compactification limit, as I will present in detail later, whereas the opposite limit would be a limit in which these branes that are present in the configuration become tensionless. And it turns out by a series of little mathematical miracles that combine together that these limits are always obstructed unless these branes are actually strings. And in this sense, the title features the word emergent strings, because these limits are really critical emergent string limits in the sense of the emergent string conjecture. So if you want a punchline for this talk, essentially is verifying the emergent string conjecture in a particular setting where supersymmetry is broken. So again, I will try to be as brief as possible, but I'm okay with questions during the talk, of course. All right, so this is the plan. Essentially, I'm going to just very briefly introduce the models I've been talking about. It's three models that are, so two of them are orientifold models, and another one is, the third model is a heterotic model. And I will mostly focus on one particular orientifold model, but the conclusions apply with minor variations to all of these. And then I will describe in particular the setup, the concrete setup where we put branes in vacuum and we see what happens. And we explicitly see a parameter that appears. It's just the number of branes that we put that describes this family of configurations that interpolate between these two infinite distance limits. And then I will describe in particular what I mean by infinite distance limits in a context where the usual exact moduli spaces that appear in supersymmetric constructions are not available. And then I will describe the final results. All right, so first of all, why would string scale supersymmetry breaking be relevant? Aside from phenomenological issues, there are theoretical motivations, namely the fact that, first of all, a very naive dimensional argument would suggest that, at least within string perturbation theory, barring some dynamical scale generation, the natural scale for things to happen, including supersymmetry breaking, will be the string scale itself. But then these perhaps naive arguments have been supplemented by a number of considerations and computations coming from the swampland side of the story, essentially supporting the idea that not only string scale supersymmetry breaking is somehow natural, but one cannot go at least parametrically low with the supersymmetry breaking scale. So all these results fit nicely together, and so they motivate the idea of looking through the landscape of non-supersymmetric string theories, in particular focusing on these ones. And among these, one can look at the closest cousins of the very well-known, or at least much better known, supersymmetric string theories in 10 dimensions. And so these diagram, as very much well known, has been augmented a little bit, featuring these three models I'm going to talk about. So first of all, the heterotic model is perhaps the simplest to understand, since it's just a rather simple projection by means of the -1 to the total fermion number operator of the exceptional heterotic superstring. And it turns out that the resulting theory is tachyon-free despite the absence of supersymmetry, and it features this particular gauge group, which will not be relevant for us. Whereas the other two models are orientival projections, respectively, of the type 2B string, where supersymmetry is broken by this projection because of the inclusions of 32 anti-D9 branes to cancel the anomaly, as opposed to the usual D9 branes with positive Ramon-Ramon charge. And the second orientival model is instead a projection of the type 0B string, which was non-supersymmetric to begin with. What happens is that the orientival projection removes the tachyon from the perturbative spectrum. So this is the construction, very briefly. Of course, if you want more details, we can talk about it. I can give you some references. But for what concerns us, we will need the low energy description of these theories, which fortunately can be given in a rather unified way. And then we will need the brane content of these theories and their interactions, of course. But first, let me tell you one reason why I'm going to focus specifically on the orientifold model coming from the type 2B string. This is called the Sugimoto model sometimes, or the USP32 model, because of the gauge group that results from the projection. So this model is rather special in comparison to the other two, because in some sense, one can say that this projection breaks supersymmetry in a spontaneous fashion. And the reason is that the low energy spectrum contains a Goldstino fermion, and whose interactions in the low energy effective action are indeed those expected from a kind of Volkov-Akulov kind of construction. In particular, the closed string sector remains supersymmetric, whereas the open string sector contains the Goldstone fermion. But in all of these models, what happens is that usually breaking supersymmetry is never something that one can do lightly. And in this case, something very dramatic happens, namely either the presence of these branes together with the orientifold plane leaves a residual tension in the vacuum, which back reacts on spacetime, of course, or in the heterotic case, the vacuum energy itself is not cancelled by supersymmetry anymore, and therefore it sources gravitational sector. And all in all of these properties can be encoded in a low energy effective potential for the dilaton that is exponential. So this back reaction, despite the absence of tachyon in the perturbative spectrum, is quite dramatic, and so we need to do something about it. And this something is exactly to introduce branes, which will lead to the constructions I've been anticipating. In particular, the low energy effective action looks like this, at least in the bosonic sector. And you see that it's just your Garden variety string theory effective action, except for the addition of this exponential potential. And the idea here is to build new kinds of low energy configurations that would not have been possible in the supersymmetric case by adding branes that source fluxes. And these fluxes can, in principle, balance out the effect of this exponential potential, producing something that otherwise would not have been possible. And moreover, it explicitly gives a chance of stabilizing this whole configuration in these models, because, of course, the expectation is that any non-supersymmetric configuration should be unstable in some way. And in our case, it is exactly this instability that will drive the theory to infinite distance limits. So all this ties in very nicely to the original point of this talk. Now, in particular, these are the branes that one can use to cook up something that makes sense in these effective theories. And we're going to focus in particular on D1 branes in the orientifold models, and NS5 branes in the heterotic model. So these two kinds of branes are the ones that produce the simplest configurations at low energies. And again, in this particular talk, I'm going to focus on D1 branes because these are the ones that will produce the emergent strings. So these are the emergent strings, or rather the dual versions will be the emergent strings in the suitable infinite distance limit. And it turns out that if one tries to apply the same logic to NS5 branes, the infinite distance limit is obstructed. And the reason it is obstructed is that instead of a 1, we have a 5. So this is really, so somehow the fact that these objects have to be one-dimensional in order for the limit to be at infinite distance seems to be quite deep-rooted in the theory, in the consistency of the theory. All right. So what do we do with these branes? So again, as I was saying, depending on the kind of model, we just put a stack of parallel either D1 branes or NS5 branes. For concreteness, let's think about D1 branes. And we just put a lot of them. And this particular flux that they source, here I'm writing everything in an electric frame kind of notation, but of course one can dualize and work with the magnetic fluxes instead. By putting this much flux, the dynamics stabilize the effective potential that results from supersymmetry breaking, and the result is that these branes produce a throat whose near horizon limit is described by an IDS Freund-Rubin vacuum. Now, this notation is fairly general, so P is just the dimension of these branes. In particular, P equals 1 would be D1 branes, so it's an ADS 3 times S7 kind of configuration. And the important bit is that for large fluxes, these configurations are weakly curved and weakly coupled, as you can see. However, as I was anticipating again, without supersymmetry to protect these configurations from decaying, decay will indeed occur. And it turns out that the nucleation rate is, as expected, exponentially suppressed in this large flux limit, but is still nonetheless there. And it's because if one computes the force between these branes in any kind of regime, this force is always repulsive. So the weak gravity conjecture is satisfied by a very non-trivial mechanism involving the parameters that enter these theories. Namely, it could have been otherwise, but just putting in the exact parameters of these theories, this force is repulsive. And in this effective theory description, this repulsive force is encoded in the rate for brane nucleation. So what happens is that these ADS vacua just gradually lose flux, and they become more and more strongly coupled and strongly curved. So on the one hand, we have this single discrete parameter n that in the large n limit describes, it can be well described by an effective field theory of gravity in this configuration. But on the other hand, the small flux limit, let's call it that, the small flux regime cannot be well described by this kind of framework. So we turn to a holographic description. And such a holographic description would be ideally, at least first proposal of it, would be given by a decoupling limit of the world volume gauge theory that lives on these branes. So the idea is that in the infrared, the world volume gauge theory that lives on these branes ought to flow to a CFT or almost CFT that would encode holographically the physics of this ADS, this metastable ADS. So this proposal for a holographic description would be encoded by just the infrared regime of this world volume gauge theory, which had been described actually long ago, but never looked at in detail in the infrared regime. And the reason is that the infrared regime of this theory is strongly coupled, because on the other hand, this theory is asymptotically free. So at least a one-loop computation, which is completely outside of the holographic regime, can still be done easily, and indeed it confirms, even though there was no guarantee in this regime, that these branes repel, even in this dual holographic description. So we have these two descriptions of these two opposite sides of the story. We have, to reiterate, a single parameter n, the number of branes, think d1 branes. We put n d1 branes in the space-time, and we have this family of configurations. At large n, we have weakly coupled description in terms of an effective field theory in 10 dimensions. Whereas for n of order 1, we should have access to a holographic description in terms of the CFT arising in infrared of this theory. So that's the idea. And so these two possible sides of the story are natural candidates for infinite distance limits in this space of configurations, right? And of course, I don't need to reiterate what Veronica has already talked about, but the idea is that at infinite distance, some kind of new description of the theory can take over, let's say a duality frame, and an infinite tower of states becomes light. And in particular, it becomes light exponentially in the suitable distance along this, this trajectory. Now, as I was anticipating in the beginning, this really, the whole flow is not necessarily under control, because for n not too small and not too big, both descriptions are not reliable, right? So it's not really clear what to do in the middle. However, both sides of the story are accessible, turns out, within a decently weakly coupled description, because the final point of this tunneling cascade of brane nucleation processes is encoded in a theory that is actually accessible. So despite this theory being generically strongly coupled in the infrared, exactly at the final point, at the end point of this process, it becomes solvable. So we have access to these infinite distance limits, and therefore we can actually compute a suitable distance in this space of configurations and see if it actually diverges. So we can see if these are actually infinite distance limits. And so as for the formalism that suggests that the holographic version of these trajectories in theory space are encoded by renormalization group flows, I listed here some of the papers, but the key point is that in the effective field theory description, in the gravitational description, in the bulk description, let's say, this is encoded by brane nucleation. In the holographic version, because of the fact that these branes repel, integrating out the relative modes in the dual world volume gauge theory, what happens is that operators that trigger RG flows appear. And so we have described these kinds of peculiar exotic RG flows in this paper, and then there's another interesting discussion on it in this more recent one. So we have these two limiting cases. And the claim is that these two cases correspond respectively, precisely as predicted by the emergent string conjecture, to a closer Klein tower and a higher spin tower that only exists in the case of D1 branes specifically, and not in the case of NS5 branes. So all this, all these words are nice, and then hopefully the pictures are too, but what do we do concretely, quantitatively? Well, my proposal, or rather, a proposal that I believe has been emerging within the community, is that a suitable generalization of the metric on exact moduli spaces is the quantum information metric applied to the space of vacua that are parameterized by the parameters of these theory space. So this concept is very general, and it has been introduced in various guises in the 90s, but recently has been revisited in this very, very nice paper by John Stout, which collects a number of ways to look at this metric, to compute this metric, and its connections to the distance conjecture. So I suggest to look at this for more details. But the idea is that the overlap between the vacua of these family of theories define this metric. And in concrete cases in which we have a description of the theory space in terms of parameters, it can be actually computed in terms of correlators partition functions. And the relevant bit is that in the two main cases where people compute distances in the context of the swampland, this metric does correctly reduce to those, namely the target space metric of the nonlinear sigma models of scalar fields in the effective supergravity theories is indeed reproduced, and holographically the metric on conformal manifolds reproduces the Zamolodchikov metric. So the idea is to use this metric on this particular trajectory in the two regimes and see if and when these are infinite distance limits and what happens in those cases. So this is the final part of the talk and the punchline. So the easy part is to look at the effective gravitational description of these ADS vacua and look at the masses of Kaluza-Klein towers along this distance. So first of all, computing this distance requires knowing the profile that the gravitation, the space-time geometry profile, and that branes produce while they repel, right? But it's not actually necessary to compute the precise behavior of this distance, because one can bound it from above and from below very easily by bounding this integral, and the details can be found in the paper. And it turns out that not only this distance is indeed infinite, it scales like log n for large n, but the masses of Kaluza-Klein states are indeed exactly exponentially suppressed. And moreover, they scale with the ADS cosmological constant precisely in the way predicted by the ADS version of the distance conjecture. So one can say that the distance conjecture is realized in these ADS vacua exactly in the way that the ADS version of it predicts. Now let's turn to the harder case, which is the emergent string limit. So I told you that this full tower of quasi CFTs that decay via RG flow into the lower flux CFTs is not under control in general, but the final part of it can be under control. In particular, the world volume gauge theories can be brought into the IR, and the infrared part of this RG flow can be actually computed. And this is because this CFT is actually very easy to describe. It's free. So let me describe it more in detail. So what happens is that when we put n equals 1 in this worldsheet field theory in the case of D1 branes, everything decouples more or less, and we have two sectors. One is a sector that flows in the IR to some complicated Vestuminovit and Cosset model, whose details can be found in the paper. But more importantly, there is a free sector described by scalars and fermions, 8 of them, because of the transverse directions to a D1 brane in 10 dimensions. And importantly, because the D1 brane is a string, so because it has 8 transverse directions, there is this spin 8 triality of the representations of these guys that produces a minimally supersymmetric superconformal field theory, albeit quite a trivial one, in this particular limit of a single D1 brane. So one recovers worldsheet supersymmetry of these branes in this limit. In the model where supersymmetry was spontaneously broken. So now that we have this free theory, we can actually look at what happens in the RG flow. And the deformation from this free theory that gives the largest distance is the closest to being marginal. And this is where we can show that this limit is at infinite distance only for D1 branes and not for higher dimensional branes, because this deformation is marginally relevant only in this case. In other cases, there are no such deformations compatible with the symmetries of the theory. And if there are, they don't give an infinite distance. So actually computing this distance is quite easy, because along this RG flow, because the theory is infrared free, the leading contribution is just a Ricci flow, because this is a nonlinear sigma model. And computing the actual distance using the formula that I showed before, one finds a very peculiar scaling with the time along the RG flow, which means that the anomalous dimensions of higher spin currents and also of scalar operators are exponentially suppressed in this distance. And again, this only works in the case in which this holographic theory is two-dimensional. So this not only reproduces the CFT version of the distance conjecture in this case, but in particular gives an interpretation that matches perfectly with the emergent string proposal, precisely because this only works for strings, and these excitations are supposed to be dual to higher spin excitations of the string. And not only that, the fact that there are scalar operators that scale in the same way suggests an equidimensional limit as required by the emergent string limit. So I think I will skip this interpretation in terms of as duality, but this is the punchline of the talk. So thank you for listening.
All right, thank you very much, Ivano. Are there questions? Okay, so while people are thinking about questions, can I ask, so in general, of course, or a priori, it's not clear that any of the swarms and conjectures keep applying if you don't have a moduli space, or if you replace it by the quantum information version. So do you think that the reason that it applies here is because you had this ADS geometry, or you had this Volkov-Akulov type breaking, or would you think that it really just is a more general statement?
Well, as far as the spontaneous breaking that you're referring to, this emergent string limit also appears in the case of the other non-supersymmetric orientifold model, in which supersymmetry is not recovered, because we didn't start from a supersymmetric theory to begin with. It was not a spontaneous breaking, if you will. And so but the emergent string story works exactly the same. What doesn't work as nicely is the idea that because one doesn't recover this worldsheet supersymmetry, interpretation in terms of a duality frame is less clear, right? Not that it's particularly clear in the case of the BSB model, but still. So I think as far as purely the emergent string story is concerned, I think it's more general. So not necessarily because it's ADS or anything. In fact, this particular quantum information metric can apply to much more general cases, in particular, for instance, to the space of space-time geometries itself in effective field theories, and it should produce results that are analogous to the ones that have been presented by the group in Munich, Dieter Lust and collaborators, who study limits in the space of metrics, for instance. And these space of metrics can be described in the same way using the quantum information metric. So I think this concept is more general. Of course, I didn't have, we just have examples. But.
Yeah, of course. Thank you. Are there further questions? I don't see any. So let's thank Ivano and Veronica again for their very nice talks.